Two sharp darts embed themselves into your skin, and in the blink of an eye, 50,000 volts of electricity flood your body. Your limbs freeze, your muscles betray you, and you collapse powerless against the invisible force coursing through you.
There you go.
This is no coincidence. It's the result of meticulous engineering designed to subdue even the most dangerous individuals without endangering their lives. This is the TASER, a device trusted by American law enforcement, developed under top-secret conditions akin to military operations.
Brother, I'm gonna fucking tase you, man. I'm gonna fucking tase you.
Created to neutralize targets with pinpoint accuracy, the TASER's become an essential tool for modern policing. But what makes it so reliable, so effective, and exclusively reserved for those who wear the badge? Let's uncover the secrets behind the rigorous production process of this extraordinary device. Don't forget to subscribe to Captain Discovery to ensure you'll never miss another exciting journey. The TASER was invented in 1969 by Jack Cover, an aerospace scientist, during the tense backdrop of the Cold War and rising crime rates, aiming to create a weapon that could incapacitate without killing. Cover drew inspiration from a fictional character, Thomas A. Swift, naming his invention TASER, Thomas A. Swift's electric rifle. The device was designed to fire two small darts that deliver an electric shock, temporarily disrupting the target's neuromuscular system. Initially, the TASER faced challenges in acceptance due to legal and safety concerns. However, in the late 1970s, with the help of entrepreneurs Rick and Tom Smith, the TASER underwent significant improvements. The brothers founded TASER International, now Axon, and transformed the device into a compact, efficient tool suitable for law enforcement.
The TASER 10 is that weapon. It begins a new era in less lethal technology.
By the 1990s, advances in battery and electrical engineering technology had made the TASER a standard non-lethal weapon in American policing. Trusted by over 18,000 law enforcement agencies worldwide, the TASER has become a symbol of modern policing, offering an effective yet humane way to resolve dangerous situations. As one of America's most iconic inventions, the TASER has helped protect millions of lives. What do you think makes the TASER a symbol of American ingenuity? Share your thoughts in the comments below. The TASER holds incredible power, but how is it made? Everything begins with the cartridge, the key component responsible for launching the electrical darts towards the target. This is where essential elements such as the compressed gas capsule, wires, and blast door are housed. Robots carry out each step with high precision, inserting the compressed gas capsule into a plastic chamber, adding a chemical primer, and sealing the protective membrane using ultrasonic welding. This process ensures that the compressed gas capsule is securely protected, ready to trigger a small explosion when needed. The entire gas chamber is then encased in an additional plastic layer before being placed inside the cartridge. Next, the wires are carefully coiled in a figure-8 pattern to prevent tangling during deployment. Technicians meticulously install the bundled wires into the cartridge, securing them neatly with a polyester membrane. The wires are then firmly connected to the barbed darts and electrodes, ensuring effective conduction of electricity. Finally, the blast door is installed in its precise position to complete the cartridge assembly. When the trigger is pulled, the chemical primer ignites the compressed gas, creating a powerful force that propels the dart into the target. Simultaneously, an electrical current is transmitted through the wires, disrupting the target's neuromuscular system and safely incapacitating it without causing long-term harm. But where does this electrical current come from? The answer lies in the body of the taser, the next step in the assembly process. The body of the taser is more than just a protective plastic shell. It houses the critical systems for control and power supply. Inside the body, a high-voltage circuit board is securely installed, designed to generate short but powerful electrical pulses. This circuit board is encased in a transparent epoxy resin to shield it from dust, moisture, and impacts. Additionally, the laser targeting system and LED lights are integrated into the body. The laser ensures precise targeting, while the LED provides necessary illumination in low-light conditions. Finally, the trigger mechanism is mounted, serving as the primary control to activate the entire system. When the trigger is pressed, the circuit board instantly powers the laser to mark the target and generates an electrical pulse transmitted through the wires inside the cartridge. This seamless integration highlights the crucial link between the taser body and the cartridge, where the high-voltage circuit board acts as the energy source for the electrical current used to incapacitate the target. With the main components ready, the final step is to assemble the device into a complete unit. The cartridge is securely inserted into the designated slot within the taser body, establishing a solid connection between the firing mechanism and the electrical system. Next, the two halves of the taser's plastic shell are joined together, encasing all internal components. Ultrasonic welding technology is used to create a seamless bond, enhancing durability while protecting the device from dust, water, and external damage. Finally, the taser undergoes rigorous testing. Every aspect of the device is examined, from the firing mechanism to the functionality of the laser, LED lights, and high-voltage circuit board. Only after passing 3 stringent tests is the taser deemed ready for deployment. With its sophisticated design and powerful electrical burst, the taser isn't just a tool, it's a trusted solution for ensuring safety in high-stakes solutions. Have you ever seen a taser in action? What was your reaction? Let us know in the comments below. Interesting facts about tasers. 1. Low current, high effectiveness. While the taser delivers up to 50,000 volts, its current is limited to just 0.002 amps, low enough to prevent serious harm, but strong enough to disrupt the neuromuscular system and temporarily incapacitate the target. 2. Shock duration. Carefully calculated. Each taser shock lasts approximately 5 seconds, a duration meticulously designed to incapacitate the target without causing lasting harm. This balance of safety and effectiveness reflects careful scientific planning. Three. Integrated camera technology. Modern taser models come with built-in cameras that automatically record every deployment. This feature supports transparency and investigation, ensuring accountability for both the user and the target. Four. Used in military training. Tasers are used in military training programs to simulate non-lethal scenarios, teaching soldiers how to manage confrontations and control situations effectively in a controlled environment. Five. Supporting firefighters in emergencies. Beyond law enforcement, tasers are also used by firefighting teams to manage individuals experiencing agitation or psychological distress during emergencies, ensuring safety for all involved. The taser has come a long way, evolving from a groundbreaking concept into an essential tool for safety and control. But with technology advancing rapidly and societal needs constantly shifting, what does the future hold for this remarkable device? Will it become more sophisticated or find entirely new applications we've yet to imagine?
With the consumer and commercial drone market expected to reach $54 billion by 2030, companies like DJI, Skydio, and Parrot are fiercely competing for industry dominance. From aerial filming and automated deliveries to infrastructure monitoring, drones are no longer just high-tech toys, they have become essential tools across various sectors. But have you ever wondered how a drone, comprising hundreds of electronic components, sensors, and complex algorithms, is manufactured from scratch? The first drones appeared in the mid-20th century, primarily for military applications. By the 2000s, advancements in autonomous flight technology, GPS, and image sensors made drones increasingly popular. However, the real breakthrough came in 2013, when DJI launched the Phantom, the first drone capable of self-stabilizing, altitude holding, and 4K video recording. This marked the moment when drones officially exploded into a multi-billion-dollar industry, spawning an ecosystem of manufacturers producing electronic components, processing chips, and control software. But behind every drone is a highly intricate production process, where aerospace engineering, electronics, and artificial intelligence converge. To gain a deeper understanding, let's explore each step of drone production, from circuit board assembly to its first flight. Every drone begins with a digital blueprint. Engineers use simulation software to optimize the frame structure, component placement, and aerodynamics to ensure the final product is lightweight, durable, and flight stable. At the same time, the flight controller, the brain of the drone, is developed. This unit processes all the incoming data from GPS, inertial measurement units, IMU, barometers, and camera systems. High-end drones also integrate AI chips for real-time image analysis, enabling obstacle avoidance and automatic flight path adjustments. A drone's frame is typically made from carbon fiber or aluminum alloy, balancing lightweight properties with structural strength. These materials are precisely cut using high-powered CNC machines, ensuring millimeter-level accuracy in every component. The technician then manually sands the edges to remove sharp surfaces. Some complex components are produced using 3D printing, optimizing the design for weight and structural efficiency. Next, workers drill mounted holes and measure their diameters with digital calipers to ensure precise alignment. Then they install the electronic speed controllers, ESCs, onto the drone's body, connecting the wiring to the autopilot system, which serves as the brain of the drone. Once all 8 ESCs are installed, the upper frame and payload mount are secured, linked to a servo motor that controls the camera's angle adjustments. Finally, the drone is enclosed with a vacuum-formed plastic cover, which is heated and molded into shape. After trimming and precisely cutting openings using CNC milling, the 4 landing legs are attached, completing the frame and control system assembly. Most modern drones come equipped with a 3-axis gimbal-stabilized camera, ensuring steady footage even in windy conditions. These cameras support 4K to 8K resolution, capturing ultra-high definition aerial footage. The camera system is linked to an advanced transmission module, which sends real-time images to the remote controller. Technologies such as OcuSync or 5.8 GHz Wi-Fi help minimize latency, allowing precise real-time control. The brushless motors play a crucial role in enabling takeoff and maintaining balance. A standard drone features 4 motors, each connected to the frame and managed by an electronic speed controller, ESC, which precisely regulates rotation speed. Next, propellers are mounted onto the motors. These are carefully designed to maximize lift while minimizing noise, ensuring optimal performance during flight. Before being shipped, every drone undergoes rigorous testing. In a controlled laboratory environment, the IMU, GPS, and barometer sensors are calibrated to guarantee flight stability. Following this, drones are transferred to an outdoor testing range, where they are evaluated for altitude retention, wind resistance, video stabilization, and obstacle avoidance. If a drone successfully passes all these quality checks, it is certified for commercial sale. Once testing is complete, the drones move to the packaging line. Each unit is placed in a shock-proof case, accompanied by a remote controller, battery, charger, and spare propellers, before being shipped to distributors or directly to customers. So, once manufacturing is complete, how does a drone operate? When powered on, the flight controller collects data from various sensors to determine the drone's position and orientation. If the user pushes the throttle, the controller increases motor speed, generating lift and allowing the drone to take off. When moving left, right, forward, or backward, the flight controller adjusts individual motor speeds, creating an imbalance in lift distribution, which tilts the drone in the desired direction. For high-end drones, AI and autonomous algorithms enable features like obstacle avoidance, automatic altitude hold, and return-to-home functions when the battery is low. These technologies make drones more accessible, even for beginners.
Each year, over 3,500 tanks roll off production lines as global defense budgets hit $2.2 trillion. But how do sheets of steel and thousands of components transform into armored machines weighing dozens of tons, reaching 70 kilometers per hour, and withstanding armor-piercing rounds? This is how the world's most advanced battle tanks are built. Tanks first appeared on the battlefield during World War I, when the British Army deployed the Mark I in 1916 to break through trench systems filled with machine guns. However, it was not until World War II that tanks became an essential weapon, with legendary models such as the Panzer, Germany, T-34, Soviet Union, and Sherman, USA. Since then, tanks have continuously evolved, incorporating composite armor, jet engines, and advanced fire control systems. Today, new generation tanks like the Abrams M1A2 SEPV3 USA, T-14, Armata Russia, and Leopard 2 A7 Plus Germany utilize the most cutting-edge manufacturing technologies. But what makes the tank production process so unique? A tank is not merely a large metal box. Its hull and turret are made from high-strength alloy steel, combined with composite materials or depleted uranium, to enhance resistance against armor-piercing rounds. Armor steel is cut using high-powered lasers or plasma to shape the main armor plates. These plates are then welded using MIG or MAG technology, with automated robots assembling the tank's hull, the primary shield protecting the crew inside. A tank requires a powerful propulsion system to traverse all types of terrain. A 1,500 horsepower diesel engine is installed, enabling the tank to reach speeds of up to 70 kilometers per hour. Additionally, a robust track suspension system allows it to navigate through mud, snow, and rugged landscapes. The tank's main weapon is a 120mm smoothbore cannon, manufactured using cold forging technology to ensure high durability. Optical sights, radar, and ballistic computers enable precise targeting, even while moving. Some modern tanks are equipped with active protection systems, APS, such as Trophy, Israel, or Afghanit, Russia, which can intercept anti-tank missiles before they hit the armor. Before being delivered to the military, each tank undergoes rigorous testing. Trial runs across various terrains: sand, mud, snow, and rocky roads to evaluate mobility. Live-fire exercises using armor-piercing and explosive rounds to assess the accuracy and power of the main gun. Durability tests, where the tank is fired upon with small-caliber weapons to check the armor's resilience. Only after passing all these tests is the tank officially handed over to the military and integrated into combat service. From a simple block of steel to a 60-ton war machine, the tank manufacturing process combines modern production technology, precision engineering, and advanced electronic systems. With the rise of artificial intelligence and combat robots, will tanks continue to be the king of the battlefield in the future? Share your thoughts in the comments, and don't forget to hit subscribe to keep exploring cutting-edge military technologies.